All right, so yeah, my name is Russell Bryan. I want to talk about SDN and Asterisk. So SDN, it's kind of like it's kind of like saying cloud and Asterisk. It's not really indicative of a very specific technology necessarily. It's more like a label that's been assigned to a larger trend, and we can dive into it and talk about different ways that manifests itself. And so I want to talk about that, some bits of technology that I think are interesting, and also try to talk about how that might relate to Asterisk in ways that you may or may not expect. So who am I? I've been a fan of Asterisk since 2004, and that's and that I've done a lot of different things in Asterisk since then. I was at one point I held the torch of leading the Asterisk project, and I helped write the Asterisk, the Definitive Guide, the O'Reilly book. And what I've been doing the last 4 years, I've been hacking on cloud infrastructure at Red Hat, and so while I've been doing that, why am I at AstriCon? Why did I speak last year and why did I speak this year? I think Asterisk is still it's super interesting to me from a personal level, but it's also interesting in my work on cloud infrastructure because Asterisk is a super interesting use case for infrastructure. I mean, I can talk to web developers and those things. It's like a dime a dozen. Super easy to talk to people about what they need for those, but communications, it has different needs from the infrastructure. So it's really interesting to be here. So I like learning about what people are doing with Asterisk and also talk to telcos about what they're doing on global scale and what they need from infrastructure. So when I talked last year, my sort of like big point to take away and what I want to and kind of what I want to continue talking about today is the future of communications runs on the future of computing infrastructure. And what I mean is, like, yeah, you need to focus on Asterisk, but you also need to look at what's happening more broadly, what's happening in the infrastructure that you're running Asterisk on, and what does that mean for you? What does that mean for designing your applications differently? What might that mean for in different ways that you can improve or get benefits and make your stuff better? So I talked about cloud infrastructure more generally, and the cloud being this elastic on-demand access to computing resources and what that might mean for scaling up and scaling down your applications more dynamically. So you need to look at designing your applications as sort of like horizontally scaled apps. I also talked about openness. I thought Dan York did a nice job talking this morning about how some of the choices we're making are leading us back towards more walled gardens and closed systems, and I think we do need to keep the importance of openness in mind, and that applies to cloud infrastructure as well. And also talked a little bit about making your apps cloud aware, but I primarily talked about compute and storage because up to that point, that's what I had spent the most time working on. But if you look at what cloud infrastructure, just the basic infrastructure as a service stuff, I mean, the core components of that, there's compute, there's networking, and there's storage. So I want to go down a little bit of a different angle on this topic, and I want to talk about the network. So what's happening in networking, and what might that mean for you? So let's. This is the only time I'll quote something from a standards site. I promise I won't do it again. But it's a good starting point. So this opennetworking.org, they have a nice page that kind of tries to capture what the trend means, and this is sort of like a top line from that. So it's the physical separation of the network control plane from the forwarding plane, and where a control plane controls several devices. So kind of a tongue twister a little bit. What does that mean? So look at the first part, physical separation of network control plane from forwarding plane. So all the things that you would consider components of your network, virtual switches running on hypervisors, your physical switches, your routers, all those things, there's sort of two functions of that. There's the forwarding plane, there's the actual packet processing, and then there's the how do you manage it, right? And so there's this sort of separation from the devices that are actually doing packet processing and what's managing all of that. And so those functions are being separated. It's being moved to where like you can have sort of this central management application that has more of a global view and insight into the network and can then manage all of the different pieces of the network and sort of dynamically change what they can do. And so another way to think about this is that more dynamic workloads require a more dynamic network. So if we think about cloud infrastructure, how you can spin things up and down as rapidly as you want. To make that all work, when you may have hundreds, thousands, tens of thousands of hypervisors, and the different components of your application are sort of scattered across all over the place there, and it's changing all the time. We need a networking system that can deal with that and can keep up with it. And so that's kind of like a big part of what's driving some changes in networks. So another point I want to make is that Asterisk's focus on better APIs is actually just a part of this larger trend. So think about Asterisk as both a thing that's the logic for call control and call processing, but also just sort of the workhorse for processing the media for calls. This focus on APIs is about more cleanly separating the workhorse telephony engine from the application control layer, and so you have a bunch of Asterisk instances, but then a separate application layer that that's using ARI or whatever to sort of control them. So it actually fits quite nicely. So one point I want to make to you is if you haven't gone to learn about ARI and thought about how you can use it to build scale-out applications with Asterisk, then please do, because I think it's important. I think it's a super valuable thing that Asterisk is doing, and I think it fits well into the larger trend of where sort of just networking in general is going. So I think the project's on the right track in that space, and if you're not already on board with there, then you should do yourself a favor. But don't just look at Asterisk for inspiration of how to move forward. I think for the Asterisk project and for building things with Asterisk, don't forget to look elsewhere. Look at your competitors and see what they're doing. Just one such example, Microsoft's Link. You say what you want about Link, if you like it or not. I don't know. I don't care. But they have a thing that called the Link SDN API. It has SDN in the name. That must mean it's good. No, but what it does is it's a nice API that lets you get access to all the information about all the different media streams that Link knows about in the system. So all the different media streams and some call quality information. And why that's valuable, think about it. If you've got a central application that wants to know everything it can about what's going on in your network, you've got, you can monitor the network itself, and you can, and maybe even have, figure out about, learn about problems in your network. But then you can use this API to get all this information about the media streams it knows about, and you can correlate call quality issues with actual network problems. So it's just about exposing more information so that some central management can do some really cool things. So getting that sort of information out of Asterisk is possible, but it's not nearly as simple as this API made it. And okay, so what I've been working on a lot is networking and cloud infrastructure. So I kind of want to go down this rabbit hole for a bit and talk about how it works, and then and some of the technologies involved in making it work. And then I'm going to come back to how some of those things relate to Asterisk. So talk about virtual networking for a moment. And cloud infrastructure, there's a difference between the way the network physically works and then the way you want it to behave more logically. So on the left side here, this is sort of representation of how the infrastructure might be laid out from a physical perspective. You've got multiple hypervisors and then VMs on both of them. But so mine might be these green VMs for my application. Yours might be the purple ones, and they're scattered around in different hypervisors. But the way we want the networking to behave is, we want your VMs to be able to talk to each other, and then I want my VMs to be able to talk to each other in some custom topology, perhaps with a router between different portions of them, and they shouldn't be able to talk to each other, right? So we need a way to be able to make this work, and also the picture changes constantly. And the reality is actually much more complicated. Beyond the fact that this picture only shows two hypervisors, at first I only said VMs, and the reality is actually containers also coming into that. And when people are using containers, they often come and go much more faster, much more quickly than VMs do. So you've got VMs and then maybe containers in VMs, or maybe containers on bare metal, and we still need a way to be able to dynamically adjust the network to provide the logical connectivity that we want. And so being able to sort of dynamically program all the different network elements gives us the ability to do that. So what does this mean for you? I mean, when you go to deploy your stuff on cloud infrastructure, it means that you can define custom network topology for your stuff, which is kind of interesting. There may be multiple reasons why you might do that. One may be that you have a physical network and physical stuff, then you want to replicate that in a virtualized environment for testing purposes and make it match your physical deployment as closely as possible. Or you may have other reasons why you want to customize your network. But the cloud, just like you can dynamically spin up and destroy your compute resources, you can do the same thing with networking. You can sort of adjust your network on the fly. In OpenStack, there's, just to show you sort of a little bit more concrete example, you go to a cloud and there's some public network you can that you start with. First, you can create your own private network. You define some subnets on that and create a router between your private network and the public network, and then perhaps allocate some public IP addresses, floating IPs, and allocate and map them to things on your private network. So that's sort of all dynamically available to you and controllable through APIs. So okay, let's go another level deeper. So that's all cool from a high level, but like, how does that work? Like, how do we build that? So one thing you might think of, and certainly the first thing I would think of is, are VLANs good enough? Is that how we build that? Maybe. It's not really a good answer. It works. It doesn't scale very well. Actually, there's a lot of problems with it. One of them is that just from a protocol perspective, you're limited to 4K VLANs at best. In reality, you're often limited to much less than that. There's lots of devices out there that won't let you have that many VLANs active at any given time. Another thing with that is it's coupling with the underlying network, meaning whenever, the workloads are dynamically placed and sort of appear and get destroyed on different hypervisors all over the place. If you're using VLANs, the way we have to make that work is we end up also having to talk to some switch-specific management interface to dynamically provision VLANs and all the different ports and all the different switches to make it all work. And it's a little bit painful. So there's another way to do it that's more scalable. It's a thing called overlay networks. So coming to networking, what do? We just throw more layers at it, right? That's how we do things. Layers that when you cut into them, they make you cry. Not really, but so overlay networks. The way this works is, first you start out with building a scalable data center network. This is actually a super interesting topic to go off and research that I've been trying to learn more about. But if you want to build a scalable data center network, the way you don't do it is provide a giant layer 2 domain for your thousands of hypervisors all to be on. You do it as you build a scalable IP network among them. Just like one term you could throw into Google if you want to go read more about this, if you're not familiar with the way people are designing data center networks, go search for spine and leaf and understand about racks and racks of servers with top-of-rack switches, and then how you might all tie all those things together. So that's where you start. And then you tunnel the virtual networks over that. And there's several different protocols for doing that. One of them is called VXLAN. This one's fairly established. There's support and NICs and servers for doing offload of this encapsulation, so you don't really take a performance hit when you do it. And we're tunneling layer 2 networks over UDP. And there's a 24-bit network identifier, so we can have over 16 million networks, which tends to be enough. And then you also have cases where you need to do a broadcast in my virtual network. How does that work when you're tunneling it over IP? Then you can use IP multicast for your logical broadcast. So it's this crazy amount of layering here, but it actually turns out to work quite well. Okay, so we've got we build a scalable IP network. We tunnel our virtual layer 2 networks over that. That's all cool. We've got some protocols to do that, but what does that look like on a given node? How do we actually make this work? Further down the rabbit hole, we need a way to program how packets are processed. So we've got a bunch of VMs, we've got tunnels to elsewhere, but the rules about how packets are processed, who can talk to who, and what security policies might be associated with that is a tough problem, and there's been some really interesting development in that area. So one project I want to mention that I've been contributing to in the last, 9 months or so is called vSwitch. So it's a production quality multi-layer virtual switch. It's an open source project, and it's designed to enable massive network automation through programmatic extension. Okay, so what is this? It's a virtual switch that runs on a hypervisor. Imagine Linux Bridge, but on steroids or something that you can program down to an incredible amount of detail and exactly how it processes packets. How this might look is, so you create this bridge We've got a few VMs on it. 2 of them might be on the same sort of logical network, like they're allowed to talk to each other, but you've got this other one that can't, and then we've got tunnels to other hypervisors. And we use this protocol called OpenFlow to program this switch. And OpenFlow, you can like build a quite advanced packet processing pipeline, matching on different fields, including the layer 2, layer 3, layer 4 fields, and completely customize how packets are sent around through the system. And that lets us, this programming of the switch can be done locally or remotely. So software-defined packet processing. Another thing I want to note, and you could do a whole talk on how OVS works. It's a super interesting project, but I wanted to note a couple things. It's hugely you can program it, but virtually most of the packet processing stays in the kernel. So there's a lot of interesting caching that's done, and for the most part, despite your ability to customize it and even do like modifications of the packets as they pass through the system, it's all in the kernel. Okay. I'm going to go a little bit further down the rabbit hole, talk a little bit more about network performance on a single host, and then we're going to come back to Asterisk. So Linux networking, this continues to change quite a bit. When we started Asterisk in the earlier days, we didn't have 10 gigabit NICs, we didn't have 40 gigabit NICs, but 10 gigabit NICs are becoming quite standard. Everyone that I talk to that's building building out data centers has at least 10 gigabit NICs in their servers. Faster is available, but I think 10 gigabit. I think we've reached a point where this is the majority of server-grade NICs being shipped is 10 gigabit. And doing packet processing at line rate, even in modern servers, is really, really hard. Doing it with small packets is harder. That's like the ultimate use case for or basically worst case scenario for can we actually process packets at this rate? And there's a lot of work going on that Asterisk benefits from all of this work, because think about what Asterisk does or what a general communications applications does. What's the media? It's a whole bunch of small packets. It's like the worst case scenario for getting best packet processing performance. There's a lot of cool work happening in the kernel networking stack, and then there's a whole other class of people that are just like, I have this like table flip, rage table flip thing here. They're just like, screw it, we'll just bypass the kernel entirely and access the NIC directly to do packet processing. Okay, so on the kernel networking stack, if you want to dive down into some really low-level stuff and learn about what the optimizations that happen there, there's a blog post here, relblog.redhat.com. Between RHEL 7.1 and 7.2, they were able to double packet routing performance, approaching 10 gigabit line rate. 10 gigabit line rate is, with small packets, is something between like 14 and 15 million packets per second, and they're getting pretty close to being able to do that, which is really fascinating. And this types of stuff they're talking, and this is all talking about RHEL, but like this is all upstream kernel stuff. This isn't Red Hat specific by any means. But the types of stuff they're talking about is like, okay, we've got like 60 nanoseconds per packet as our time budget, or like 100-something CPU cycles. I mean, the level of optimization they're doing is just fascinating and way over my head. But check it out, because I'm in awe of the amount of work that's still left to be done to optimize packet processing. So another sort of recommendation is like, maybe you shouldn't still use that Linux distro you started using 8 years ago. Like maybe you should maybe like as a super cheap improvement you can make is upgrade and get the benefits that all these people are working really hard, because like small packet processing is the thing that benefits most from this kind of stuff. So consider upgrading. So kernel bypass. This is another sort of like super interesting topic that you can go dive off and research. There's a project called DPDK, it stands for Data Plane Development Kit. This thing was started by Intel, and so to Intel, they're shipping these super fast NICs, and they actually want them to people to be able to utilize them. So they have this thing that it does all the packet processing in user space, bypasses the kernel entirely. You typically dedicate one or more CPUs to it that are just constantly pulling the NIC. And well, it's fast, and it does show better networking performance. There's a lot of downsides to it. The biggest one to me is that by bypassing the kernel, well, you don't get anything that the kernel network stack does. It turns out there's been a lot of people working on networking stack here, and it's a whole lot of hard work that's been done there, and just kind of like saying, oh, never mind, we can just do it all ourselves, is not the most obvious win. But the target use case is generally very, very targeted applications. So, and the people asking for this the most are telcos, right? So think about these large-scale telcos that have lots and lots of servers doing tons of small packet processing. So they're trying to squeeze every bit of performance out of servers they can. And so they want things like this, get the performance benefits. So that's cool stuff. Another thing you can do is, you can get hypothetically, you can get the best of both worlds. You can, there's a thing called queue splitting, the bifurcated driver. This is a very new thing. And you can do both. So you can have most of your traffic go through the Linux networking stack, but you can have a subset of it, and this is programmable, using DPDK. So, for example, maybe you want every packet that matches the UDP ports that you're using for RTP to go through DPDK and do your RTP processing that way, but everything else through the typical network stack. So that's a good use case for why you want to do something like that. Okay, so I dove way down a rabbit hole talking about how the data path in Linux is, one, there's a ton of interesting performance work happening, but two, there's a ton of interesting programmable extensions to the data path that have happened that let you customize what the way packets are processed in the kernel. So what could that mean for Asterisk? Well, Asterisk does lots of packet processing, especially with RTP. So what might we be able to do? So there's a project called RTP proxy. When people start talking about larger scale Asterisk deployments, you've got Asterisk, you might have Chameleon, and then an RTP proxy. That's it's just a project that literally is just proxying RTP. You might need that if you want all of your media to pass through sort of a controlled point at the edge of your network. Maybe we could rebuild that using DPDK. If I wanted to have that function in the most sort of ultimate amount of performance, this is how I do it. Now it's a lot of work, but you could do it, and the telcos are doing this. This is exactly why they want DPDK. So this kind of thing could actually take off quite a bit if anyone was interested in such a thing. Another way we might think about it is, well, what about Open vSwitch? Open vSwitch sort of, you're not talking to the NIC directly and doing everything yourself. Maybe this is enough, or maybe we can extend it to do some more, to proxy RTP, program the data path in the kernel to do the proxying of RTP. Now, I talked about OVS and the way packets are, the default data path for OVS is all through the kernel. You can also use DPDK as the backend for OVS. So maybe we can do RTP bridging in the kernel. And I wonder what kind of performance improvements we could get from that. Can we just program the virtual switch to forward RTP streams as needed? And that, my friend, sounds like a very dangerous demo. And with that, I'll say thank you very much. And so I may or may not have a demo tomorrow showing RTP processing in the kernel with a pretty drastic, surprising amount of performance improvement tomorrow. But that's just a tease. And for now, I can take any questions you might have. I think I've got about 5 minutes.
So I've actually got a question.
OK.
You talked about layer 2 tunneling over UDP. Mm-hmm. And my question is, what do you do when you start approaching the MTU? Does the MTU shrink in the guest, or do you end up just fragmenting?
That's a really good question. So you have a mic so everyone heard the question. So what happens with the MTU? You shrink the MTU in the guest. Okay. You need to leave space to add the encapsulation. And so typically, I think you can do it with a DHCP option. I think that's what we normally do is tell it tell it that the MTU is 1420 instead of 1500 or something like that, or whatever whatever the physical network MTU is minus some space for the encapsulation. So.
Gotcha. Cool.
Yeah.
Thank you.
Fascinating. Very good question. That's that's a super common thing that people that goes wrong when people start trying to play with this stuff.
All right. What are the questions we have for Russell?
All right. Well, I'll be around all day, week. So if anyone wants to chat about cloud infrastructure, or networking, or the old days of Asterisk, I don't know, any things like that, then feel free to grab me. Thank you very much for coming. I really appreciate it.